infimum and supremum of a set of numbers are two key concepts in theory of real numbers. That's why it's so important to understand them very well. Perhaps the best way to do this is to start from the simpler concept of minimum and maximum of a set. In this video, we will focus on minimum and then on the infimum of a set. Maximum and supremum can be handled similarly, and I warmly suggest you to work out the details. So let's take a set S of real numbers. The minimum of the set is just the smallest element of the set. Formally, we say that M is minimum for S if M is smaller than each of the elements of S and it belongs to the set capital S. A major applied problem consists in, given a set S, determine the minimum of the set. Actually, the existence of the minimum is not always granted. For example, we can easily prove that if the set S is finite, then the minimum exists, and we also have a simple algorithm to determine the minimum. Let's represent the set by a finite list of numbers, let's say S1, S2, etc., S capital N. And let's proceed as follows. We define a temporary minimum as the first element of the list. Then we start comparing the temporary minimum with all the other elements. And when we find one of the elements of the list which is less than the temporary minimum, we just replace the temporary minimum with that element. At the end of this procedure, the element M will be the minimum of the set S. But what happens if the set S is not finite? That is, as we say, it is infinite. Well, in this case, it is easy to prove that, in general, it is not granted that the minimum exists. And in fact, we see here an example of a set which has not a minimum. We take the set of numbers 1 over n, where n is natural, greater or equal than 1. So these are particular fractions. We can help the intuition with a sort of figure of this set of numbers in the real line. It is clear that we have numbers which are positive because fractions 1 over n are positive. So they are at right of 0. And for n equal 1, we have 1 over 1. For n equal 2, we have 1/2. For n equal 3, we have 1/3. For n equal 4, 1/4, and so on. 1/5, 1/6, etc. We cannot, of course, plot all of these numbers because they are infinitely many. What we can easily verify here is that there cannot be a minimum for this set. Let's see why. If a minimum exists, so if M is the minimum of this set S, then this M should be first less or equal than all fractions 1 over n for n natural and greater or equal than 1. And second, it must be one of the elements of the set. So it means that it is one of these fractions. So there is an n that we call n hat, such that our M is equal to 1 over n hat. But now we see that these two conditions together cannot stay together, because if we take the element 1 over n hat plus 1, well, this element belongs to the set S, and it is clearly less than M, which is supposed to be the minimum. And this is in contradiction with the first property. So this proves that this set has not a minimum, and in general, the message is that minimum of S might not exist. However, if we look at this example, we may realize that something interesting happens. Well, look at the number 0. The number 0 is not in the set, so it cannot be a minimum. It is a number which is at the left of the set, so all the elements of the set are larger than him. And it has another special property, which is it is the biggest number that verifies this condition to be at left of the set. So in other words, it is what we could call the best of the lower bounds, so the bounds from below to the set S. So this means that 0 is, first of all, a number which is less or equal than each of the fractions 1 over n. And second, no matter how you take a number which is greater than 0, so let's say a number like this one, this number b is no more a lower bound. So it is no more at left of the set, in the sense that there exists at least an element of the set, a fraction 1 over n, which falls at left of b. So these two characteristics are the characteristics of the infimum, or the best lower bound of the set. So we say that a number m is the infimum, or best lower bound, of S if, first, the element m is at left of each of the elements of the set, is left of the set, so m less or equal than S for every S in the set. And this is the same first property for the minimum. But the second property is different. We do not require that m belongs to S, otherwise we would have the definition of minimum, but rather we require that m is the best to verify the first condition. The best means that if I take a number b which is greater than m, then this b is no more at the left of the set. So there is some element of the set which is at left of b. And this is what is the infimum of the set S. There is a relation, of course, between minimum and the infimum. For example, you can easily prove that if the minimum exists, then it is also the infimum for the set. However, as the example we have discussed above shows, there are cases for which there exists the infimum of the set, but there is no minimum. In that case, the set of numbers 1 over n and natural greater or equal than 1, the infimum is 0, while there is no minimum for the set. So what is the message? The infimum is an extension of the operation of minimum, with the advantage that while minimum is not always defined, infimum in real numbers always exists. And this is a consequence of completeness axiom. This has a number of advantages and consequences, both on theoretical and practical side.